Okay, so I may have forgot to turn on the microphone during recording, so I have to record my voice later, and it may not be of sync. So yeah, so XML is a measure space. So in the previous lecture, we defined a setup. So we saw that we couldn't do it for the whole power setup R, the problem of measure that we want. So we need proper setups to do that. So there is just measurable spaces. And now we define the function analogous to the props, just one analogous property to the given function, and that's the main property we want. Is if mu is a function from m to close 0 comma infinity, if the empty set mu is 0 and mu is countably additive, that is disjoint if you take, then it breaks into a sum. Yeah. So also there is a slightly weaker condition that if it is not a measure, if it's not countably additive, but if it's finitely additive, that is um, yeah. So if mu of finite disjoint union from 1 to k an is summation 1 to k mu of an. So clearly every countably additive, so every measure is finitely additive, but not the other way around. We will give an example of such a measure. So for all an measure. So while I do this, the arithmetic that I have in mind for close 0 comma infinity, that infinity is an upper bound of this, and infinity dot 0 is 0, and infinity plus an ideal number is infinity in close 0 comma infinity. So now two important properties that we that I leave. The first one I leave it up to you. So if A is less subset of B, then mu A is less than or equal to mu of B. This is called monotonicity. And second is this is called countable subadditive. So if we do the disjoint thing, so mu of a countable union an is not equal, since we are dropping the disjoint, but we get less than equal to summation 1 to infinity mu of a. And to obtain this, we do something that is called the standard disjointification technique. So suppose en equal to union 1 to n a k, then disjointify them, define fn plus 1 equal to en plus 1 minus en. So clearly fn's are disjoint, and fn plus 1, I wrote it wrong here, fn plus 1 is subset of an actually, n plus 1. So so union en is equal to union fn for the finite sum. Obviously for finite sum it is union 1 to an, and for the partial sums also. So hence mu of disjoint union fn is same as mu of union 1 to infinity an, and since it is disjoint, it is equal to summation mu of fn, and since fn is contained inside n, it is then equal to summation mu of an. Right. So this is that this is countably subadditive. Countably subadditive. This is less than equal to, yeah, so I make the change here. Yeah, so I make the change here. There are some problems in syncing because I am turning the radio. Sorry for that. I will try to keep the microphone on. Next one, and this one is the important one. So here, what next? So there are many pathological examples of measures. So but we will mainly work with measures that are found most natural and most applicable, that are finite and sigma finite measure. So XM is a measurable space, and with a measure it is called a measure space. So if the measure of the whole set is finite, then it is called a finite measure space. And there are examples of spaces which are so what is an example of finite measure space? Well, we will give an example of finite measure space. So, and there exists A belongs to M, such that this is example of sigma finite. So sigma finite means it's not finite but as good as it. So if there is a measurable countable collection of elements in F sets in M, that each of them has finite measure, and their union is the entire space. So X can be written as countable union of finite measure sets. This is called finite, this is called sigma finite, this is called countably sub-additive, and this is called monotonicity. This is called countable additivity, and this will just be language to us for the lectures now on, and this is called finite additivity. So the first question is, give an example of a finite measure. So take X and take the indiscrete measure on it. This is called the indiscrete measure probably. So this is a sigma algebra, and define mu of X to be any positive real number you want. So this is an finite measure. Suppose 1 or anything that you want. So 1 has a special name. If the measure of the space is 1, then it's called a probability space. So we will study later. And if you want to example of that is not finite, just take mu of X to be infinity. So simple, but so let's give example of a sigma finite space. Well, a finite measure space is always sigma finite. So let's try to give an example of a measure space that is sigma finite but not finite. Well, the example we use a very important example. This is called so its natural number and power set of n is the measurable space, and mu c is called the counting measure. So mu c of S gives the cardinality of S. So if S is finite, we get the cardinality. If S is infinite, we get infinity. And thing is, there is nothing special about natural number. We can do it over any non-empty set. This is the counting measure. So if the set is finite, then it is finite, and what the length is, what the cardinality is, and what's infinite, uncountable, countable, anything, it is infinite. And you can easily see that this is a measure, because if you take a disjoint union, countable union, so if any of them is finite, if the disjoint union, well, if any of them is infinite, then it is infinite only. So right side and left side are both infinite, because and if all of them are finite, then it's just the sum. Disjoint union is just the sum. So yeah. So now we do an important proposition, that is, if X comma M be a measurable space, then, well, I will write the following are equivalent, but it's not actually true. We won't able to show 3 implies 1. It is true if X if it's a finite space, if it's finite measure. So okay, mu is assumed to be finitely additive here. So mu is mu satisfies 1 and 3. So it's called finitely additive set function on a measurable space. So these are equivalent. Mu is measure 2 if we are given ENs belonging to M, so that En increases in means in terms of inclusion. So it's a decreasing chain and its union is E, then mu n converges to mu in mu n converges to mu in real numbers. So you can give the topology on closed 0 comma infinity as a one, what is the one point computation of closed 0 comma a, and you don't actually need to, you know, where sequences converge to infinity and stuff, right? So, and the third is if so this won't imply 1. So third is if mu e1 is less than infinity, that is it's finite, and en is a decreasing chain up to e, that is this intersection, then mu en converges to mu of e. It's a decreasing sequence also. So the first one is the increasing sequence and the lower is a decreasing sequence, so it converges somewhere, either infinity or somewhere. And so let's go into the proof. So first one implies 2. So suppose mu is a measure, then define en increases up to e, then do the standard disjoint integration technique. So define f1 to be e1 and fn plus 1 to be en plus 1 minus en. So yeah, so fn is subset of en, that is clear. So now mu of, and this is true for partial sums also, that is union fn equal to union en. So mu of e is equal to mu of union en, this is equal to mu union fn, disjoint union of mu union fn. So and this is summation 1 to infinity, which is the disjoint, and we are given it's a measure fn, and this is just, we can write limit n tends to limit k tends to infinity, summation 1 to k mu of fn, and since it's a measure, it's finite derivative, it's given a finite derivative, so this is limit n tends to infinity mu of ek actually, mu of, yeah, so mu of 2 implies 3 is quite easy. So yeah, this is because of it. So 2 implies 3 is quite easy. So okay, so one thing I forgot to give in this lecture is a condition when it's not finite, that is 3 means continuity from doesn't hold if mu1 is, if all are infinite. So okay, that example I will give in the next lecture. So en decreases up to e, then e1 minus en increases up to e1 minus e, and then mu e1 minus en by continuity from above. This limit is mu of e1 minus e, and since it's finite, you can break it actually. Even if it's not finite, you can break it if one of them is finite, if the lower one is finite, but still okay, mu of e1 minus mu of en, this will be with limit, and we don't need to worry that all of them are finite. And the next thing is limit n tends to infinity mu e1 minus mu e1. Now since mu1 is finite, we can cancel it, and hence we get is continuity from above. Yeah. Now 3 doesn't imply 1, so we will show that how 2 implies 1. That is quite trivial actually, so we will show how 2 implies 1. So suppose we take a disjoint union of ens, so mu of so suppose En is a disjoint collection, and take Fk to be disjoint union 1 2 K F E K. So En, then union En, mu of this. So this is same as union disjoint union Fk. Not this is not disjoint. I said the other way around. This limit and tends to infinity by continuity from above, from the second one. Mu of Fk and mu by finite additivity that is given, that is summation 1 to mu of Ek, because Fk is disjoint union 1 to K Ek, and from here this is nothing but the uncountable sum. So here we are done. So 3 doesn't imply 1, and why we will give an example such as how 3 does not imply 1. So suppose there exists a measure space where continuity from above holds, that is its name is a measurable space. We use finite derivatives at continuity from above holds, that is for every finite set. If it decreases, then limits also commute, and which shows the space, but mu will not be a measure. So take natural number, take power set of natural number, and take a measure which is known as cofinite measure probably. I may be wrong. So mu is defined in this manner. So mu prime, let's say, is to be mu prime of A is 0 if A is finite, and infinity if A is not finite, if A is infinite. So this is clearly measure. So if you take union so that 1 is not finite, disjoint union so that 1 is not finite, then the right side will also be not finite. So once 1 will be infinity, so entire thing will be infinity. And if every one of them is finite, so this is not a measure, this is finite entity. So if you take a finite disjoint union of finite sets, it is also finite, so both sides agree. But it is not a measure because natural number is infinite, so it can be written as finite union of singletons. So those are, so under countable unions, this is not this is does not have countable additivity. So mu is a finitely additive set function, but not a measure. So we will show that continuity above still holds here. So suppose mu n is mu1, E1 is less than infinity, so it can be 0, right? So it means E1 is finite. So En decreases to E, then this is a decreasing chain of finite sets. So since mu is 0, that is 0, so mu n's all are 0, this is 0. So this is a constant sequence of zeros which converges to 0. So continuity from above always holds, but this is not a measure. So continuity from above doesn't imply a measure. And since I have time, since I'm doing actually a voiceover, so let me give a quick hint of how to work with the hypothesis necessary. So take natural number, power set of natural numbers, and counting measure to show why the hypothesis in that is necessary, that mu1 must be infinity. So suppose I will give an example of a measure. So let me write whatever I did. So the hint is natural numbers, power set of natural numbers, and counting measures. So take ik to be natural number minus 1 2 up to k. See, it's a decreasing chain. Each measure is finite, but the intersection is the empty set, which is 0. So continuity from above doesn't hold. So now we'll define something known as the complete measure. So I will not do it in the next lecture. You can hear it from here. So try this. So xm comma mu is said to be complete if it contains all subset of null sets. So what do we mean by null set? Null set is something whose measure is 0. So it's complete if all subsets of null sets are there in the measure in the sigma algebra. So they're kind of compatible and it's quite useful nature. So um, suppose so an example of a non-complete measure will be, so define everything to be 0 on this sigma algebra. So that's a very trivial example that we give. We will give non-trivial examples later. We'll give example of sigma finite measures that are not complete. In fact, Borel sigma algebra is not contained, but we haven't defined a measure on that. We need to construct. After we construct that is a Lebesgue measure, we will show it's not complete. And yeah, so every measure actually may not be complete, but it has a completion. So what do you mean by completion? So completion means that every measure is contained inside another measure space which is complete, which extends it, and it is the smallest complete measure contained. What is that? I write it in mathematical in a language now. So mu bar restricted to m is mu, and so m bar contains m, mu bar restricted to m is mu. So mu is what is an extension of mu, and extension is complete. And it is called a completion if it is the smallest of its kind. That is, if x bar x comma m bar bar comma mu bar bar is another complete measure that extends xm bar from mu bar is another complete measure that extends xm bar comma mu bar, then this is said to be xm bar comma mu bar. This is it. This is the smallest one. This is the, so it is contained here. That's why it's called the completion. So the proof is simple. So what we do is forcefully create a sigma algebra that consists of all the null sets. So it must contain M, it must contain all subset of null sets, so it must contain their unions. So let's start with that. Let's create a sigma algebra with the union of an element in the sigma algebra N and a null set. So define M bar as all such A union is, so that A belongs to M and E is a subset of a null set. E subset of N, where N is a mu null set, what I mean, means mu of N is 0. So clearly you can see M bar is closed under count. M bar contains M, and M bar is closed under countable unions because AK union EK, this union, this union AK union in EK, and union EK is containing union NK, which is in the sigma algebra, and since by countable subadditivity this is also a null set, so it's closed under countable unions. So what we need to check is the complementing. So A union E complement is A complement intersection E complement. E complement is contained in E is contained inside N. So E complement can be written as N minus E union N complement. N minus E union N complement. So from there it follows that this is A complement intersection N minus E complement, and this is A complement intersection N complement, and this is intersection N minus E intersection N complement, and this is so this is in the sigma algebra, the first part, because it is intersection of two elements in the sigma algebra, and the third part is subset of N, so it's a null, so it is subset of a null set. This will be union set. Yeah, so this belongs to M bar. So now that we have proved that this is the sigma algebra, we need to define mu bar on it. So if mu bar needs to be defined, it needs to extend mu. So if mu bar A union E, this must be by, if the measure is less than equal to mu bar of A plus mu bar of E, mu bar of E must be less than mu bar of N, mu bar of N must extend, so it must be 0. So there is only one choice to define it. So this is mu A. So, well, there is no other way to define it, but we need to show that this is well defined. This definition is well defined. Suppose A1 union E1 is equal to A2 union E2, that is the same representation of the same set. So if A1, yeah, here what I made the problem, I thought that the Bluetooth is on. A union E equal to, suppose A1 union E1 equal to A2 union E2, and where E1 is subset of N1 null set and E2 is subset of N2 another null set, then A1 is contained in A2 union A2 by countable subadditivity. Since the measure of N2 is 0, this implies mu of A1 is less than equal to mu of A2. Other way round, we get mu of A2 is less than equal to mu of A1, so it's well defined. So this is the measure, and you can easily check that this is a measure, follows from mu being a measure, right? And it is the smallest measure is quite easier, because if there is another complete measure extending this, then the method we shown M needs to be there, the null sets need to be there, so the union needs to be there, and if it extends mu, then it needs to be mu A on these sets, so it needs to be that on M bar. So this is the smallest complete measure. So this is the completion. So yeah, so in next lecture we will try to develop, now the machinery is set, we will try to develop one of the first fundamental theorem, that is the Carathéodory extension theorem, to try to give the construction of the Lebesgue measure. Yeah.